Welcome everyone, good day, and a blessed day. Today, we will delve into one of the foundational concepts of linear algebra, which is the basis of a vector space. Are you all excited? Before we start, I want to introduce first myself. My name is Nelson P. Santos, and I will be your teacher for today. Before we start our discussion, let's have first our learning outcomes. This will be our roadmap for our discussion. First, define a basis of a vector space, understanding its rule in representing vectors uniquely. Second, determine if a set of vectors spans a given vector space, relating it to the concept of a basis. Third, understand the concept of linear independence and be able to determine if a set of vectors is linearly independent. Fourth, determine whether a given set of vectors forms a basis for a vector space, providing proof or justification. I hope you are all excited for our discussion. Let's go! Before we will delve into the main part of our discussion, let's start first with the history of basis in linear algebra. The concept of basis in linear algebra traces its roots back to the late 19th and early 20th centuries, evolving alongside the development of the field itself. As mathematicians delved deeper into the study of vector spaces and systems of linear equations, the need for a systematic way to represent vectors became apparent. The notion of a basis began to take shape with the work of mathematicians like David Hilbert, as you can see on the picture, who in the late 19th century laid the groundwork for modern linear algebra. Hilbert's work on the foundations of geometry and his formalization of vector spaces provided a crucial backdrop for the concept of basis to emerge. Wow! Like what we always do, let us define first the word basis. According to the presentation, a finite set of vectors, the set v sub 1 up to v sub m, is called a basis for a vector space if the set spans V and is linearly independent. According to the definition, we have two conditions for a set of vectors to be called a basis. The first condition is that it spans V, and the second condition is that it is linearly independent. Now, to understand these two conditions, let's start first with the definitions of span, and then after which is the linearly independent. The definition of span is presented on the screen. The vectors v sub 1, v sub 2, up to v sub m are said to span a vector space if every vector in the space can be expressed as a linear combination of these vectors. So under span, we have another condition, is that it should be expressed as a linear combination. In this case, v sub 1, v sub 2, ellipsis v sub m is called a spanning set. If we achieve this condition, then we can say that the set is a spanning set. Now, let's take a look at the definition of linearly independent. The set of vectors v sub 1 up to v sub m is linearly independent if c sub 1 v sub 1 plus ellipsis plus c sub m v sub m is equal to 0 can only be satisfied when c sub 1 is equal to 0 up to c sub m equal to 0. Now, to understand these two definitions, let's take a look at some examples. Let's take a simple example to understand basis. So we have to show that the set 1, 0, 1, negative 2, 1, 4, 0, 3, 1 is a basis for R3. Since this is three-dimensional, we are expected to find three linearly independent vectors. Now, the first thing that we need to do is to check whether our column vectors is linearly independent. Okay, so how are we going to do that? So So we will gonna transform these column vectors into a matrix. So as you can see, this is the transformation of our column vector for R3. Now, the next step here is that we should get an identity matrix through row reduction. Okay, so what do we mean by that? Wherein our diagonal should be equal to 1 and that the remaining parts of our matrix should be equal to 0. So that's why we will use row reduction to achieve that. So the first thing that we're gonna do is to make our third row first column equal to 0. So by doing that, we are going to do this operation. We have to multiply -1 from our row 1 and add it to our row 3. Now the result, by doing this operation, we have 1, -2, 0, 0, 1, 3, and 0, 6, 1. As you can see, the first row and second row are not changed. Okay, it's only on the third row that our matrix changed through this operation. Now -1 times R1, that is -1, plus our row 3, we have 0, since -1 plus 1 is 0. The next step is we have -1 times -2, we have +2, plus 4, that is equal to 6. Next, we have -1 times 0, that is 0, plus row 3, that is 1. So that's why our row 3, we have the values 0, 6, and 1. Now, since we've achieved this one, our main focus now is on column 2, since we already have 1, 0, 0 for our column 1. Now, our next target is to make -2 and 6 equal to 0. So let's target first number 6. Now, to do this, we are going to multiply -6 to our row 2 and add it to our row 3. Now, -6 times 0, that is equal to 0, plus 0, we have 0. Now next, -6 times row 2, that is -6 times 1, that is -6, plus 6, that is equal to 0. And then next, -6 times 3, that is -18, plus 1, that is -17. That's how we get the third matrix for our solution. And next, for our column 2, is that we should make -2 equal to 0. So to do that, we are going to multiply +2 from our row 2 and add it to our row 1, since our goal here is to make our -2 on row 1 equal to 0. Now we are going to do the operation. 2 times 0, that is equal to 0, plus 1, that is equal to 1. That's why on our fourth matrix, 1, okay, didn't change from our solution. Next, 2 times 2 times 1, that is 2, plus -2, that is equal to 0. And the next, 2 times 3, that is 6, plus 0, that is equal to 6. So here is the result of our operation. Now, the next step here is to make our third row, third column, which is the -17, equal to 1, since our goal here is that our diagonal should be equal to 1. Now, what are we going to do? We multiply this with 1/17, which is its inverse. Now we have here -1/17 times row 3. So we have any numbers multiplied to 0. We know that is always equal to 0. That's why the first two elements on our matrix is equal to 0. So -1/17 times -17, that is equal to 1. So only row 3 change based on our operation. Now here, we have the next step. Our main goal in our third column is to make 6 and 3 equal to 0. So our first target here is 3. So what are we going to do? We are to multiply -3 from our row 3 and add it to our row 2. So -3 times 0, that is 0, plus 0, that is still equal to 0. -3 times 0 is still 0, plus 1, that is equal to 1. Next, -3 times 1, that is -3, plus 3, that is equal to 0. Now, our matrix already changed. Now, next is to make 6 equal to 0. So, what are we going to do? We multiply -6 from our row 3 and add it to our row 1. And for the result, let's take the next slide. doing the operation on our last slide, we will achieve this result. So here we have 1, 0, 0, 0, 1, 0, and 0, 0, 1. Now we've already achieved an identity matrix based on our operation. Here we have 3 pivots which indicate that the sets are linearly independent. So we've already proven that our set is linearly independent since we achieve here at 3 pivots based on row reduction. And take note that under a theorem on columns of identity matrix, actually an identity matrix forms a basis. And since this is an identity matrix, so we've already achieved, okay, our goal, which is to prove that this is linearly independent and even a basis. Another way of knowing linear independence of matrices is by getting its determinant. So there is already there's another step again, or another way of doing this thing. So here, if we compute for the determinant of the given matrix, we will actually get a negative 17 as the result. So if you want to do that, you can do it on your own. If the determinant actually is computed 0, or the result is 0, the given set of matrix is categorized as linearly dependent. Okay, so if the determinant is 0, we call it as linearly dependent. But if we get a number greater than or less than 0, we call it as linearly independent. So there are many ways in actually proving linear independence of a matrix. So first is through row reduction, another is through computing its determinant. So we've proven a simple example under basis. So here, let's take another example, and we will use the conditions that is given a while back. Okay, if we remember, our condition for a basis to be called for a set of vectors to be called a basis is that it should span and it is linearly independent. In our first example, we just proved it as linearly independent, though we call it as a basis through identity matrix or through the theorem on column of identity matrix. We will provide another example so that we can actually see the relationship and the weaving of this definition on basis. Let's take example number 2 and use the two conditions on basis. So let us show that the set 1, 0, negative 1, 1, 1, 1, and 1, 2, 4 a basis for R3. Now, based on the conditions as presented from the definition on basis, it should span and that it is linearly independent. So let's take first this solution wherein our set spans. So we have to consider particular elements of our R3 that if we substitute any value here, we could still generate, okay, an answer. Now our goal here is that we are going to represent x sub 1, x sub 2, and x sub 3 any elements on our R3. Now we are going to equate this, and here we have a sub 1 times 1, 0, negative 1 plus a sub 2 times 1, 1, 1 plus a sub 3, 1, 2, 4. If we note, based on the definition of span, it should be a linear combination. And now under linear combination, we have scalar quantities that if ever multiplied from the sets or from the elements, we could still get a particular element, or there should not be an error, or it should not be unknown. So here, our goal here is that we should find values for a sub 1, a sub 2, and a sub 3. Now to do that, we are going to equate our set, or our this one, into a sub-equations, if I'm correct. So here, we are going to prioritize first our first element on sets. So for x sub 1, we have a sub 1 plus a sub 2 plus a sub 3. Now how did we get these values? So if we multiply a sub 1 from the first element, which is 1 on the set, we have a sub 1. And then we have a sub 2 times 1 is a sub 2. A sub 3 times 1, we have a sub 3. Since we refer on our x sub 1 as the first element, so we are going to consider the first element on this particular set. Now let's proceed on x sub 2. Now here, x sub 2 is equal to a sub 2 plus 2a sub 3. Now how did we arrive with these values? So here, a sub 1 times 0, since we are considering the second element, so we are going to multiply our scalar quantities a sub 1, a sub 2, and a sub 3 on this element. So here, we have to multiply a sub 1 on our second element, since we are referring to x sub 2. Now a sub 1 times 0, that is 0, that's why we cannot see any a sub 1 from our second equation. Now let's proceed on the second part. So we have a sub 2 times 1, so we have here a sub 2. And then next, a sub 3 times 2, we have 2a sub 3. So we got this value. Now next is on our third element, so we have x sub 3. Now how did we arrive with these values? The same step. A sub 1 times our third element on the set, we have negative 1, then we have negative a sub 1. And then a sub 2 times 1, we have a sub 2. And last, we have a sub 3 times 4, we have 4a sub 3. So that's how we arrive with this solution. Now, let's go with this one. Now, how did we arrive with this? We have here, we have already proven that a sub 1, a sub 2, and a sub 3 have values. And since these scalar quantities have values, then it means that the set spans. Since we've already proven that this is a linear combination, so it already spans. Now, how did we arrive with these values? Right, so that's the question. Because as you can see on this one, there are a lot of intricacies. Okay, and then it proceeds with this one. Now let's go over on the next slide and see the detailed solution on how we arrive with a sub 1, a sub 2, and a sub 3, or their values. Okay. Here is the detailed solution of our answer on the previous slide. So here we will refer x sub 1 as our x sub 2 as our y, and x sub 3 as our z. So for the first step, we are going to find a sub 3 by adding first equation 1 and equation 3. So here is the solution. So here is our equation 1. So as you can see, x sub 1 from here is already changed to a sub 2x. And for our x sub 3, it's already changed to z. So here is the equation. Now here we're gonna add our two equations. And as a result, we have now here as the final answer 2a sub 2 plus 5a sub 3, which is equal to x plus z. So here we haven't yet find the value of a sub 3. Now our second step is find here. We have to subtract twice equation 2 from the new equation. So we have now here, okay, our equation, okay, that we got from this from the first step. And here is an equation from this one, our second equation, which we multiply it twice. So 2 times a sub 2, we have 2a sub 2. 2 times 2a sub 3, that is 4a sub 3. And 2 times x sub 2, which is equal to y. Okay, we change it to y. We have now 2y. Here, we are going to operate now by subtracting our equation. So 2a sub 2 minus 2a sub 2, that is equal to 0. And then 5a sub 3 minus 4a sub 3, that is equal to a sub 3. X, and then minus, so there's no equal variable, so we are just going to bring it down. So we have x, then we have minus 2y, and then we have plus z. So the value of a sub 3 is equal to x minus 2y plus z, which is equivalent to a sub 3, which is equal to x sub 1 minus 2x sub 2 plus x sub 3. Okay, so later we will go back with our first slide and see if our answer is correct. Now for step 3, we are going to substitute a sub 3, okay, the value that we got from our second step, and substitute it back into the second equation, since it's more easier if we have the lesser variable. Now we are going to find a sub 2 through substitution. So here we have a sub 2 plus 2 times, since we already have the value of a sub 3, so we just substituted here in our equation, and now equal to y. So we have to expand or do the distributive property. So we have 2 times x, that is 2x, 2 times negative 2y, that is negative 4y, and 2 times z, that is 2z. Now here, we're going to transpose or get the inverse of all these elements, or just transpose it as the easiest way. So we got the value a sub 2, which is equal to negative 2x plus 5y minus 2z, which is in original form, we have a sub 2, which is equal to negative 2x sub 1 plus 5x sub 2 minus 2x sub 3. So we've already got the value for a sub 3 and a sub 2. And the only thing that we haven't found yet is the value of a sub 1. So let's go and find a sub 1. Now here is the solution for a sub 1. So we are now on our step number 4. So we are going to substitute a sub 2 and a sub 3 on our first equation. So if we substitute it, we will arrive with this equation. So we have a sub 1 plus, we have the value for a sub 2, plus we have also the value of a sub 3, that is equal to x. So here, by just doing the particular operation, so we have a sub 1 plus, or since we have here negative 2, so it's just we have minus 2x. And then plus 5y minus 2z plus x minus 2y plus z, which is equal to x. So by combining similar terms, we will arrive with this answer. We have a sub 1 minus x plus 3y minus z, which is equal to x. Since we are just looking for the value of a sub 1, we just need to transpose the values. So the values x, 3y, and z on the other side of the equation, since that's the easiest way, or we could just have its inverse and just do the property, right? And then now we have our final answer, which is a sub 1, which is equal to 2x minus 3y plus z. Now here, the original form of our equation will be a sub 1, which is equal to 2x sub 1 minus 3x sub 2 plus x sub 3. Since we are able to express x, y, z as a linear combination of the vectors in our set for any x, y, z, an element of our R3, then the set 1, 0, negative 1, 1, 1, 1, 1, 2, 4 spans R3. So we've just finished proving the spanning part of our set, and we are on the next condition. So actually, this is quite rigid, since you're doing a lot of things, but I hope you followed our steps a while back. So we have 4 steps in doing the spanning. Now let's see if we got the same answer based on our solution on the previous slide. Okay, let's check. As you can see on our presentation, we've got the same answer from the detailed solution on the solution on spanning. So here is the solution we got from the detailed part, and this is the solution presented from the example number 2 on the first slide. So here, a sub 2 is equal to 2x minus 3y plus z, and which is equivalent to 2x sub 1 minus 3x sub 2 plus x sub 3, which we just converted, since on our equation before, or a while back, wherein x sub 1 is equal to x, y is equal to x sub 2, and z, which is equal to x sub 3. So if you want to validate, so you can just scan through or just have your inspection on our set of values. As you can see, we've proven that our detailed solution aligns with the solution from our presentation. So it means that the set really spans R3. Now we are going to proceed on the next part, which is we need to prove that our set is linearly independent. Let's go. Now let's take on the second condition of our thesis, which is to test whether our set is linearly independent. So we have to consider the same values a while back, which are 1, 0, negative 1, 1, 1, 1, and 1, 2, 4. So here we have to equate our equation by 0, 0, 0, since our main goal is that for our identities, we will get 0 as their values. So the same is true is happened with our span. We are going to do it also in our linearly independent solution. Wherein for each point from 0, 0, 0 from the first, second, and third, we're gonna get their values through our original equation. So we will also base it as from the first points on each particular set. So we have the first point first. So b sub 1 times 1. For the first point, we have b1. b sub 2 times 1, we have also b sub 2. And b sub 3 times 1, we have b sub 3. So we are through with our first point. Now let's consider the second point. We have b sub 1 times 0, that is 0. So we cannot say b sub 1 from this part. Next, b sub 2 times 1, we have b sub 2, and b sub 3 times 2, we have 2b sub 3. So the same step based from our span a while back. So it's just that we have zeros as our, as the end of our equation. So here, as you can see, we will get b sub 1, which is equal to 0, b sub 2, which is equal to 0, and b sub 3, which is equal to 0. And this is a unique solution. Now, as you can see, the detailed solution is not presented on this slide. So we will present it later. But since we got 0 for each value of b sub 1, b sub 2, and b sub 3, then we can say that the set is linearly independent. So we can say that 1, 0, negative 1, 1, 1, and 1, 1, 2, 4 spans R3 based on our solution on the first part and now is linearly independent. This means that our set forms a basis for R3. Now let's take a look at the detailed solution for b sub 1, which is equal to 0, b sub 2 equal to 0, and b sub 3 equal to 0. So how did we arrive with this kind of values? So let's take a look. So here is the detailed solution of our last presentation. So here we have 3 steps for this presentation. We are going to prove why b sub 1 is equal to 0, b sub 2 equal to 0, and why b sub 3 equal to 0. So we will use our solutions or our from our the 3 equations from our previous presentation. So here we are going to add equation 1 and 3 so that we will get values. So we have here 2b sub 2 plus 5b sub 3 through this one. Okay, so for our first equation, we have b sub 1 plus b sub 2 plus b sub 3 equal to 0. And our third equation, which is negative 1 b sub 1 plus b sub 2 plus 4 b sub 3 equal to 0. Since our main goal here is to eradicate one variable, so here we have to add b sub 1 and negative b sub 1. And as a result, we got these values. And for step 2, we are going to subtract twice equation 2 from the new equation so that we can omit or we can cancel out 2b sub 2 from the solution or from the answer a while back. So here we're going to get twice our equation 2. So 2 times b sub 2, we have 2b sub 2. 2 times 2b sub 3, we have 4b sub 3, which is now equal to 0. So here by subtracting, we got the value b sub 3, which is equal to 0 from 5b sub 3 minus 4b sub 3. So we have here the solution. So we've already found the value of b sub 3. And now let's proceed on the remaining 2 values, which is b sub 2 and b sub 1. And for our presentation, we have here b sub 2. So what are we going to do? We will substitute b sub 3 back into the second equation. So we have b sub 2 plus 2b sub 3, which is equal to 0 from our second equation. And by process of substitution, we have b sub 2 plus 2 times 0, that is equal to 0. So we have b sub 2 equal to 0. So that's how we found the value of b sub 2. Okay, now for the last part, let's move on to the next slide. And now for our last step, we are going to find the value of b sub 1. So as you can see, we just substitute the value of b sub 2 and b sub 3 from the solutions we had a while back. So here we have b sub 2 equal to 0 and b sub 3 equal to 0. So by process of substitution, we will just be left on the value of b sub 1, and we have here equal to 0. So we have found that the only solution to the system of equations is b1, which is equal to b2, and equal to b3, that is equal to 0, which means the set 1, 0, negative 1, 1, 1, and 1, 1, 2, and 4 is linearly independent. So you can see, we have just proven that our set is truly linearly independent. One example is not enough, so I mean two examples isn't enough. So let's take on another example, which is, I think, much harder. So we are going to show that the functions or the set f, g, h, where f of x is equal to x squared plus 1, g of x, which is equal to 3x minus 1, and h of x equal to negative 4x plus 1, a basis for p sub 2, wherein our polynomial is of degree 2. Now, here, just like what we did on our example number 2, we are going to prove our functions if they span and if they are linearly independent for them to be called a basis, right? So let's take first on the first part, which is the solution for spanning. So we have to let p be an arbitrary function in p sub 2, and p is thus a polynomial of the form p of x, which is equal to bx squared plus cx plus d, since we are involved with polynomial with degree 2. Okay, so we are to suppose that the function is equal to a sub 1 times the function of x plus a sub 2 times the function of g of x, and plus a sub 3 times the function h of x. So for some scalars, we have a sub 1, a sub 2, and a sub 3. So our main goal here is that we should find a value for this particular scalars to be called or to be categorized as this set really spans. So this gives us the value bx squared plus cx plus d, which is from here, okay, the value of p of x just substituted from our equation. Now, we have now to provide the value of our function. So a sub 1 times the function f of x, which is equal to x squared plus 1 from the original or from the given. So just substituted here from our equation, okay, that we generated. And then plus a sub 2, which is the g of x, value of g of x, we have 3x minus 1, and a sub 3, we have the value of h of x, which is negative 4x plus 1. So what we did on the first part of our equation is just we substituted the values of f of x, g of x, h of x, and even p of x. Okay, so by process of, distribution, or the distributive property, so we have a sub 1 times x squared, we have a sub 1 x squared, and then a sub 1 plus 1, that is equal to a sub 1, right? So it's here. So we have a sub 2 times 3 of x, we have 3a sub 2, and then we have also a sub 2 times negative 1, we have negative a sub 2. We have a sub 3 times negative 4x, we have negative 4a sub 3, and then we have we have a sub 3 times 1, we have a sub 3. So here is just, what do you call this one? Grouping, okay, grouping of similar terms. Okay, we just factor it out. So for the first one, there's no factor. We have a sub 1 x squared plus 3a sub 2 minus 4a sub 3. We have here the value, which is their commonality, the common factor. We have 3x a sub 2 and 4x a sub 3, so their common factor is x, that's why it's outside our equation. Plus, we have our points a while back. So as you can see, our equation is now in the format of a function, right? Our degree 2. So we have x squared plus x plus a constant. So let's proceed on the next part. Now, the next part of our solution. So here, we separated our factored form of our equation into 3 equations. So we have now a sub 1, which is equal to b. We have 3a sub 2 minus 4a sub 3, which is equal to c. A sub 1 minus a sub 2 plus a sub 3, which is equal to d. So we have now a system of equation. Now here in our presentation, we already have the solution for a sub 1, a sub 2, and a sub 3. As you can see, a sub 1 is equal to b, a sub 2 is equal to 4b minus 4d minus c, and a sub 3, which is equal to 3b minus 3d minus c. So as you can see, we found the value for a sub 1, a sub 2, and a sub 3, and now we can say that the functions f, g, and h span p sub 2, since we got values for our scalar quantities. Now, the problem is how did we arrive with this values for a sub 1, a sub 2, and a sub 3. Now, let's go over with our next slide for the detailed solution. We are on the last part of our solution. So this is the detailed solution of our answer on the previous slides. As you can see here, we have already found the value of a sub 1, which is equal to b. This is the three equations we generated from the factored form of our original equation on the previous slide, right? So here, we are left with a sub 2 and a sub 3. So we need to find those two in order for us to evaluate whether our set spans. So here we are going to add equation 2 and thrice equation 3. So here is our equation 2 and this is thrice the equation 3. Okay, so if ever we will add this one, we will have the following answer. So you have 3a sub 1 minus a sub 3, which is equal to c plus 3d. Now here we don't have a sub 2 since 3a sub 2 plus negative a sub 2 is equal to 0. So we are just left with a sub 1 and a sub 3 for this new equation. Now for step 2, we are going to substitute the value of a sub 1 for our three equations here. We have a sub 1 which is equal to b, which is substituted from the new equation. So here we have 3 times b since we already substituted a sub 1 from the new equation minus a sub 3 which is equal to c plus 3d. Now here, if we transpose the other values, we will have the value of a sub 3 which is equal to 3b minus c minus 3d. Now we already have the value of a sub 3 and we are left with the value of a sub 2. So here we are going to substitute the value of a sub 3 which we had a while back and substitute it to the second equation. So here we have 3a sub 2 minus 4 times the value of a sub 3 which is 3b minus c minus 3d now equal to c. Now here we have through distributive property, we're going to distribute 4 to the terms inside our parentheses. So we have 3a sub 2, we'll just copy, and negative 4 times 3b, that is negative 12b, negative 4 times negative c, that is positive 4c, and negative 4 times negative 3d, that is equal to positive 12d. Now, if ever we transpose our values on the other side of the equation, we will be left with this answer. We have a sub 2 which is equal to 4b minus c minus 4d. Now, if ever we want to evaluate whether the 3 are correct, so you can just refer it on our previous slide. Now, we are through with the solution on span, and we are left with the second condition, which is to test whether our set is linearly independent. Let's proceed. Let's move on the solution of linear independence. So we have here our three equations. So unlike our spanning, which we equated them from ABC, or B, C, D. Okay, sorry. We have B, C, D. For linear independence, we have to equate our equations into 0, since our main goal here is that we should generate scalar quantities that are equal to 0. So what we mean is we have to find a value for a sub 1, a sub 2, a sub 3 that should be equal to 0. And here is the detailed solution for linear independence. So we have step 1, we have to add equation 2 to thrice equation 3, which is similar with our first solution with under spanning. So here, if we add equation 2 to thrice equation 3, we will get the values 3a sub 1 minus a sub 3, which is equal to 0. Now let's proceed on the next part. We'll proceed with step 2. We are going to substitute the value of a sub 1 to the new equation. So the value of a sub 1 a while back is equal to 0. So we have 3a sub 1 minus a sub 3, which is equal to 0. So we have 3 times 0, that is minus a sub 3 is equal to 0. And 3 times 0 is 0, so negative a sub 3 is equal to 0, and by transposition, we will get a positive 1. We have a sub 3, which is equal to 0. And for step 3, we have to substitute a sub 3. From the second equation, we have 3a sub 2 minus 4a sub 3, which is equal to 0. And by process of substitution, we will now substitute a sub 3 that is equal to 0 from the equation. So we have 3a sub 2 minus 4 times 0, which is equal to 0. So we are left with 3a sub 2. So dividing both sides by 3, we will get a sub 2, which is equal to 0. So as you can see, we got a sub 1 that is equal to 0, a sub 2 that is equal to 0, and a sub 3 which is equal to 0. So this just means that our set of functions f, g, and h are linearly independent and even a span. So this means our function or our p sub 2 is a basis. Congratulations! Summary of our lesson. We have here the presentation. So on our topic under linear algebra, which is basis, we have actually two conditions which we discussed. Wherein the first one is that it spans V, and the second one is that it should be linearly independent for it to be considered a basis. And now for spanning, the thing that we did a while back is that we should get a value for a sub 1, a sub 2, and a sub 3. That is for spans. But for linear independence, our scalar quantity a sub 1, a sub 2, and a sub 3 should be equal to 0. Okay, so under spanning, there should be value, but for linear independence, it should be equal to 0. Okay, so that is the basic identity of a basis under linear algebra. So we are just finished discussing the basis, and I hope you learned a lot from my presentation. So understanding basis allows us to navigate vector spaces with precision and clarity, providing the tools to manipulate and interpret multidimensional data effectively. So by mastering the concept of a basis, one gains a deeper insights into the structure and functionality of linear algebra and its wide-ranging applications. So I hope you learned a lot from our discussion, and if ever you did not understand some key concepts, some process, you can just go over it. For the application of basis, we have here bases are crucial in various applications such as solving linear equations, transforming coordinates, and simplifying complex problems in engineering, physics, computer science, and more. So basically, linear algebra or the topic basis is not solely for mathematics, but this can even be applied through engineering, physics, and even computer science. Always seems impossible until it's done, by Nelson Mandela. Yeah, right. A while back, it's so confusing, it's so complex, but through the process, but through undergoing it, we can actually achieve it. God bless everyone, and thank you for listening.